Hey everybody, today's video is going to be about randomness. Now, there are a lot of interesting things that I can say about randomness. There's a lot of things you can say about it in a philosophical sense, so there's a big debate about if randomness is even a real thing, and it's a conversation that's linked quite closely to quantum mechanics and quantum theory. Can everything be predicted? This can tie into like questions of free will and determinism. It's not really something that I'm going to get into too much in this video. I'm going to tackle randomness more from a mathematical perspective. And specifically, I'm going to try and argue that it is not a well-defined concept in a lot of different situations. So I'll give you an example of where randomness is well-defined. And by well-defined, I just mean that we understand what it means, or I could speak of randomness and there would be no lack of clarity as to what I mean. So if I give you a puzzle that says, take a deck of cards and, shuffle it and take the top 5 cards in the deck, what are the odds that you make a full house, for example? A full house being a 3 of a kind and a 2 of a kind. We could do that, right? So I've got a deck of cards here. I could easily shuffle it up and I could take the top 5 cards. And I can check if it's a full house. But it's not a full house. It probably wasn't going to be. I'm not going to actually do the math to solve the question of what are the odds, but there is a solution. And you can use combinatorics to find it, or you can try and approach it with a simulation where you just simulate it billions of times and count the number of full houses you generate. That's well defined. There's no ambiguity as to what I mean by shuffle the deck and take 5 cards off the top. Now, likewise, you can pick random items from an infinite field, or a continuous field, I should say, and have no ambiguity. So, for example, there might be some puzzle that involves picking a random number from 0 to 1, right? So from this range 0 to 1, pick a random number. You might pick 0.937, or you might pick 0.784. These are all going to be, I guess, theoretically going on forever. Now, even though there are an infinite number of solutions to this problem, the question is still well defined. Pick a random number from 0 to 1. In the same way we can speak about, throwing a dart on the dartboard and thinking, what are the odds that it's going to land in a certain region of the dartboard? Now, sometimes randomness isn't well defined. And here is a very famous example of where it's not well defined. This is called Bertrand's paradox, and it is to do with chords in a circle. So in a circle, a chord refers to a line connecting 2 points on the circumference of the circle. So for example, this is a chord. There's a chord of the circle. This here is another chord of the circle. That could be quite small like this. Now, the question is, and actually I've got it written down here. We're going to start with the puzzle based on this shape. So picking a chord on a circle, what's the probability that the chord is bigger than the side length of the inscribed equilateral triangle? So you'll be able to see that on this circle I have inscribed an equilateral triangle. So because it's equilateral, it means that all these angles are going to be 60. And it's the biggest equilateral triangle, and in fact the only one that I can fit inside of this perfect circle. So picking the chord on the circle, what's the probability that the chord is bigger than the side length of the inscribed equilateral triangle? So for example, if I pick this chord, I should use the line tool. If I pick this chord, it won't be bigger. But if I pick this chord, it will be bigger. You can see this line here is clearly bigger than this line here. All right. So you can probably see where I'm going with this, but to solve this question, we have to know what we mean by picking a random chord. What does it mean to pick a random chord in a circle? And I'm going to propose a couple of ways that we could pick a random chord in the circle. Firstly, and this might be quite an intuitive idea, is we pick one random point on the circumference, and then you pick another random point. And from any 2 random points, we can connect a chord. So this is one way that we can pick a random chord on the circle. So if that's our generation method of picking random points, without losing any generality, let's just say that our first point happens to be here, exactly on this point here. And then let's think about where our second point can be selected. Well, if our second point is anywhere here in this region, the resulting chord is going to be less than the side length of this equilateral triangle, because again, this is the side length, so if it's anywhere here, it'll be lower. So for example, this would be lower. But if it's in this other region here, it will be larger. So this is quite straightforward. We can just think about the percentage chance that it's going to be in this red section versus this orange section, and the answer is 1/3. So already from our first method of selection, we found the probability is equal to 1/3. Cool. Now let's think of other ways that we can select a random chord. Let's say, for example, that to select a random chord, we are going to select a random radius from the center of our circle, and then a random distance along that radius. So this is our center. When I say pick a random radius, I'm more talking about picking a random angle. So for example, the angle might go out this way, and then I pick a random point along that angle, like say this point here, and then I draw a perpendicular line, and hopefully you can see how with this generation method I can generate every possible chord. Well, let's analyze it. Well, without losing generality, again, because the circle is symmetrical, let's just say, for the sake of argument, that my radius is selected like this. And now the question is, what length of chords do I generate based on where I pick along the radius? Well, if I pick this point, my resulting chord will be here. Clearly it's smaller than the side length of my equilateral triangle. But if I pick it here, then my resulting chord is clearly larger. And in fact, what you'll see again is that anything selected in this region will give me a larger chord, and anything in this region will give me a smaller chord. So it seems like the odds now are 1/2. So 1/2. This is kind of weird, right? Because we propose two very valid methods of selecting a random chord. Each method is capable of selecting any chord, and yet they gave different answers to the problem. Now I'm going to propose a third solution as well, and that is to pick a random midpoint of my curve, my chord. What I mean by that is I pick a random point in the circle. Let's say I pick this point here, and then I connect my radius through it, and then again I do this here, and this second line I draw on becomes my chord. This is not unlike my second method that I did, except this time I'm not bothering with picking the radius and then picking a point on the radius. I'm just picking the point. So I pick any random point in this circle, and we'll speak later on about how we can define this as well. Say I pick it here. Because it's a point in a circle, I can draw a line connecting it to the center, and then a perpendicular line will give me my chord. So let's think again about the odds. Well, I'm not going to get too into the proof of this because it's a bit more complicated. If you have some basic geometry skills, you should be able to figure it out. But what we end up finding is that if the initial point that I pick is in this circle here, which is the biggest circle we can fit perfectly inscribed inside of my equilateral triangle, if I pick any point in here, then when I form my chord, by going this way and then cutting through here, my chord will be bigger than my equilateral triangle side length. However, if I pick anything outside of the circle, like this, the result will be smaller. So the answer to our frequency is basically just going to be the odds that I pick a point in this circle as opposed to in this outside region here. Well, we can solve that. I mean, this circle is going to be has half of the radius of the bigger circle. So let's say the biggest circle's radius is r. It's going to be pi r squared. It's going to be the total area of the shape. And for our small circle, so this is for the big circle, for our small circle, it's going to be pi times half of the radius squared, or r on 2 squared. And because we're squaring, it's going to end up with pi times r squared on 4, which is also the same thing as saying pi r squared on 4. The point that I'm trying to make here is that the small circle has exactly 1/4 of the area of the large circle. If I divide pi r squared by this value, I will get 4. So the answer is a fourth. So I'll add that into my set of answers. Cool. Alright, so I think you kind of get the point now. All three of these methods are perfectly fine methods for finding a chord of the circle. They're all completely fine. Every possible chord can be found with one of these methods. But there is no... But they all yield different answers. So clearly something's going on, and that is that the way we pick our random object matters. This is what I mean by defining randomness. What we say is that the distribution of chords in a circle is not uniform or is not well defined. Basically, this question is an invalid question. You're not allowed to ask this without defining what you mean by picking a random chord in a circle. Cool. All right. Well, I'm going to give a much more simple example now before I get into the final part of this video. I suppose I can rub this out now. Pick a random number. Pick a random integer. In fact, pick 2 random integers. Actually, no, pick 3 random integers, a, b, and c. A, b, and c. And I might just ask you something like, what are the odds that a plus b equals c? Well, there are a lot of ways a plus b could equal c. Like maybe if a is 1 and b is 4, c would have to be 5. Maybe if a is 3 and b is 3, c could be 6. There's an infinite number of ways this can be true, but there's also an infinite number of ways it can be false. And I think the answer to this question is actually technically going to just be 0, which is to do with the fact that there's just way more ways that it could be false than be true. But what I'm getting at is that the idea of picking a random integer is not well defined, right? It doesn't mean anything to pick a random integer because there's no maximum integer to pick from. I could say pick a random integer from 0 up until a massive number, right? This is well defined because there's a maximum. But pick a random integer from 0 to infinity is not well defined. Because what's even the average going to be? How can I analyze this? What's the average integer I pick? Is it going to be half of infinity? Well, you'd think so, right? It has to be halfway through the number line, but then this doesn't mean anything. This isn't a number. Also not well defined. If I ask you to write some Python software that picks a random integer and I run it over and over again, I can guarantee you that all your answers are going to be far closer to 0 than any large number that I could make up. They're always going to be closer to 0 than infinity, whatever that means. Alright, one final puzzle, and this is also to do with randomness and also to do with circles. So I spoke a little bit before about picking a random point inside of a circle, and I just want to expand a bit more on that with a puzzle. This is a circle. Now, can you write an algorithm that picks a random point in this circle? And when I say write an algorithm, I mean like maybe a Python script. It doesn't really matter. Just in theory, can you write an algorithm that picks a random point in the circle? And there's one rule. There's one rule. The algorithm must have a theoretically bounded runtime. I haven't got into sort of the coding concepts too much yet on this channel, but this is something called Big Omega or Big O, which is a computer science concept. It's to do with runtimes of algorithms. Basically what I'm saying is that whatever algorithm you write, it has to come to a close in a predetermined maximum amount of time. It can't theoretically run forever. So let me tell you give you an example of what I mean by that. Well, a sort of naive approach to this problem would be to say, well, why don't I pick a random point in this square? And I'm just going to make sure my square is drawn quite fairly. Okay, we're going to just assume that, imagine the square like perfectly inscribes a circle. I can pick a random point in the square quite easily, because that's just the same thing as picking two numbers from 0 to 1. So I've got 0, 1 here, I've got 0, 1 here. And then I can pick the point that it generates, and then I can basically check, is that point in the circle? And if it is, I can output it, and I found it. If not, I can pick another one. And then see, is that in the circle? And if it is, I'll output it, and if not, I'll pick another one. Now, this solution isn't valid because it doesn't have a theoretically bounded runtime, because I don't know how long it will last, right? The first 10,000 points I pick may all be not in the circle. It's very unlikely, but it's possible. And what I'm getting at is that there has to be a strictly finite runtime for my algorithm. So how can you do it? What other methods can we do? Well, why don't we forget about the square, and let's say we pick a random radius. That's fine, because you're just picking a number from 0 to 360, or a number from 0 to 2 pi if you want to use radians. You're picking a direction for the radius, and then you're picking a distance across this radius from 0 to 1. So for example, you might pick 0.4, which is about here, and you've selected this point here. That could be your method of selecting the point. Now notice that that method should be valid because it always runs in the exact same amount of time. It doesn't require any repeats. It always gives you a point in the circle. But does it give you a random point in the circle? Does it give you a random point in the circle? That is the question we have to ask ourselves. And it's hard to show you why it doesn't without giving a simulation. But it doesn't. And the reason it doesn't is because it's way easier for this algorithm to output points close to the center. So it's going to pick way more points around this belt here, and it will get a lot more sparse out here. There'll be less of them out here and more in the center. So it's not truly random. And the reason that's the case is because if I pick any number, say, less than 0.5, I'm going to output a point inside of this circle here, right? It's about halfway through. If I pick anything greater than 0.5, it's going to output something in this ring here. So there's a half chance that my point I generate is in here, and a half chance that it's not in here. But notice that these aren't the same area shapes, right? And as we've already established, actually, this is only a quarter of my shape, and this is 3/4 of my shape. So it's not a fair distribution. So again, that doesn't do it. It's an invalid method because it doesn't pick a purely random point. So what can you do? What is the solution? And I'm sort of tempted to not even give this solution and just leave it as an exercise, but I will give the solution. This is the only solution that I have found to this problem. And that is to do what we've done. Pick a random radius, that's fine. That's not the issue. Pick a value from 0 to 1 along this line, and then take the square root of it. So say if I pick 0.31, take the square root of 0.31, and then go to that. That's the actual point you use. So you actually, the square root of 0.31, I don't know what it's going to be. It's going to be bigger than 0.31. It's going to be, let's say it's 0.6. I don't know. It doesn't matter what it is. You go to 0.6 instead. And that's your point. Because we've got a problem here where when we pick points in our earlier solution, the points get biased towards the center. And by square rooting your number, you completely undo that bias. Keep in mind that when you square root a number from 0 to 1, the number actually gets bigger, not smaller. So the square rooting operation is always going to push points this way down the line. It's basically going to reverse the bias we have of points being closer to the center. It's going to reverse the bias, make it more fair again. Now, why square root? This is something I'm tempted to leave as an exercise, but it has a lot to do with how it's pi r squared. has a lot to do with how the area of circles grow with a squared factor. And in fact, this squared factor is the exact factor that biases the points towards the center of my circle. So by square rooting my value along the radius, I completely mitigate that. And that's an idea that you can formalize more on your own. It's a good exercise. Cool. All right. I think that's basically all I've got to say about randomness. I might speak more in a different video about philosophical randomness, but this is just sort of problems with randomness in math. But yeah, anyway. Cheers, guys. Thanks for watching.